Hi, welcome back to the Chapter 2.3 video lecture series. We're looking at one quantitative variable and measures of spread. So the last video we went over a standard deviation, how to calculate it, and some applications. We're going to keep going and looking at standard deviation and the 95% rule. This rule says that if a distribution of data is approximately bell-shaped, so that means symmetric and unimodal, one hump, about 95% of the data will fall between two standard deviations of the mean. So this within two standard deviations, that is above and below. So if we have a bell-shaped population, 95% of the data will be between the mean minus 2 times the standard deviation and the mean plus 2 times the standard deviation. So this is really a spread of 4 standard deviations in the middle. Will give you 95%. So visually, if we take a perfectly bell-shaped distribution, the center is going to be the mean, and we can move over to 1. This would be the mean plus 1 standard deviation, and the mean plus 2 standard deviations. And then on the left side of the mean, we have the mean minus 1 standard deviation, and the mean minus 2 standard deviations. And this range, the bulk of the population or the sample, 95%, should fall within this range. All right, so if we were to take these two distributions that are fairly bell-shaped, symmetric and unimodal, here we have a standard deviation of 1. And notice the center of this distribution is 0. So this is saying if I move over down 2 standard deviations and up 2 standard deviations, so 2 times standard deviation is 2. So if I look at all the data from minus 2 to positive 2, that should encompass a bulk or about 95% of your data right here in this kind of fat middle part. And if we go with the standard deviation is 4 for this larger spread distribution, I would still say the center is right around 0, maybe minus 1 to 0. The center, if we're going to subtract 4, the idea is we're going to go down to minus 8 or so, all the way to positive 8. And this value here, this minus 8 to positive 8, should give us about 95% of the distribution. Okay, so what if we try to work this backwards? Here we have a distribution that's fairly bell-shaped, symmetric and unimodal. Can you estimate the standard deviation for hours of sleep per night? All right, and we can't get an exact answer, but out of these 4 options, plus that I have no idea, the best guess here is going to be 2. And the exact value is 2.03, but we would need the actual data set to compute the actual value. But see, how do we get that? I like to say if we look at the middle of this distribution, or maybe I forget the middle. I might better think, okay, what 2 scores on the bottom are going to separate 95%? And that to me looks like it's between 2 and 10. So actually, I want to write a couple things down here. Last example. Let's just scroll to the next page. All right, so we have here in this distribution, it looks like the 95% of the observations of the data are between 2 and 10. So we have bell-shaped distribution where about 95% of the data lies within 2 to 10 hours. All right, just kind of putting to typing up what I was saying right here, 2 to 10 hours. That's the bulk of the results. Well, this range of 10 minus 2 equals 8 encompasses 4 standard deviations. 2 below the mean plus 2 above the mean. So a good estimate for the standard deviation is going to be 8 divided by 4, because we have those 4 standard deviations. That's why about a good guess of that distribution is we should have about a standard deviation of 2. All right, so based on some student survey data, pulse rates for the sample of college students are approximately bell-shaped. We're going to assume that bell-shaped distribution with a mean of 69.9 and a standard deviation of 12.12. What interval is likely to contain 95% of all pulse rates in the sample? And what we want to do is take this mean and add and subtract 2 times the standard deviation. So it's the mean plus or minus 2 times the standard deviation of 12.2. If you take 69.6 plus 2 times 12.2, that gives you the 95 beats per minute. If you take 69.6 minus 12.2 times 2, that gives you the 45.2. Again, don't forget this only really works for if you have a bell-shaped distribution. All right, another topic we're going to look at is Z-score. So the Z-score for a data value x is given by the formula below. Z is the difference between x and the mean. Hopefully that looks familiar. We calculated this when we did standard deviation. But then we're going to divide that by the standard deviation. For a population, x bar, it will be replaced with mu, and x will be replaced with sigma. So same formula, but z is a data value minus the mean divided by standard deviation. So the idea is that z-scores put values on a common scale. If you're comparing different groups with different averages and different standard deviations, you can calculate z-scores to compare all of them together. Values farther away from 0 are more extreme. 0 z-score is the mean. And a z-score is the number of standard deviation a value falls from the mean. So going back to that 95% rule, if we have a bell-shaped distribution, then about 95% of all z-scores should fall between 2 and minus 2. All right, let's look at an example. Which is better, an ACT score of 28 or an SAT score of 2100? And all we know is that the ACT has an average of 21 with a standard deviation of 5. The SAT has a standard mean of 1500 and a standard deviation of 325. So the idea of a z-score, if we calculate z-scores for these values, we're going to end up with a way to compare these two values. All right, so let's see how we get why the SAT score is actually a better score relative to their groups. If we take the ACT score of 28, subtract the mean away from 28, and then divide by 5, we get 1.4. If we go through that same process, if you get 2100 on the SAT and subtract the mean away from that, and then divide by the standard deviation, you end up with a 1.85. All right, so I'm going to learn a little extra about this problem. So ACT z-score for 21 is z equals, what was it, 1.4. So this means a score of 21 on the ACT is 1.4 standard deviations above the mean. And we look at ACT z-score for 2100. That is the z equals 1.85. So a score of 2100. Oh, sorry, this should be 28 up here from the previous slide. That should be 28 as well. Ooh, okay, so typo. So we're looking at a 28. So So 28 minus 21. Sorry, okay, so 28 gives you a 1.4 standard deviations. 2100 on SATs is the 1.85 standard deviations above the mean. What does a z-score of minus 1.5 mean? You can have negative z-scores, you can have negative test scores, but it would mean, let's say on the ACT, this means the score is 1.5 times the standard deviation below the mean. So we could calculate that. All right, we've got z equals 1.5. So then the value would be the mean minus 1.5 times sigma. So if we're looking at ACT, that would be 21 was the average, minus 1.5 times the mean, which was 5. I'm going to throw that in my calculator. 21 minus 1.5 times 5 would be 13.5. So this is saying a score of 13.5 on ACT is, or say corresponds to a z-score of negative 1.5 because it's 1.5 standard deviations below the mean. All right. So the z-scores are really nice because this is called standardizing or normalizing scores. All right, so we're going to look at other measures of location. Two fairly obvious ones: maximum, minimum, largest data value, smallest data value, and quartiles. Q1 is the median of the values below this M is the median. And Q3 is the median of the values above M. So these are the textbook's definition, but I like another way to think about these quartiles. We haven't clearly defined percentiles yet. We will later in this chapter. But Q1 is the 25th percentile, and it's a number that separates the bottom 25% of the data. So if you were to sort your data, this 25th percentile separates the bottom, the lower 25% of the data. And Q3 is the 75th percentile. And it's a number that separates the bottom, lower 75% of the data. So it's another way to think about this. I actually like these definitions a little bit better. Think about splitting up your data into quarters, basically. That's why they're called quartiles. And put together, we have a 5-number summary. This is a nice kind of quick snapshot of how your data distribution looks. Starts with a max and a min. Then we're going to look at the median value. So the exact center, or not the exact center, I should say, because there's different measures of center, but the data point that separates the data into 2 different sets. And then the 25th percentile, the Q1, will separate the bottom 25%. And then we have Q3 separates the bottom 75%. Notice right here, between each of these, this 5-number summary will be 25% of the data, of the observations, of the responses are going to be between the min and Q1. 25% of the data will be between Q3 and the max. All right, let's look at one more example. We're getting close to 15 minutes, so we're going to come back and look at this example in the next video.